Okay, so this is part 2 of the periodic table video. So we talked in the last little section about the alkali metals, group 1, and we're now going to come across here to group 7, which contains the halogens. So let's see what we need to know about the halogens. So in group 7, the halogens, we have got the following elements. We have got fluorine, chlorine, bromine, and iodine. Okay, and one of the things we need to know is the colour of these elements. So these elements, we have got fluorine is a yellow colour, chlorine is green, bromine is red brown, and iodine is grey. Iodine gives off a purple vapour, but it's a grey solid, which links in with the second thing we need to know, which is the state at room temperature. We need to know what state it will be at room temperature. If I've got fluorine in this room here with me, this is going to be a gas. Chlorine is also going to be a gas. Bromine is a liquid, and iodine is a solid. So what does this tell me about the trends in their physical properties? It tells me that as I come down this group, because we're going from gas to liquid to solid, and what we're getting here is that the melting and boiling point is increasing. Okay, and that's why we get this change in state. Also, thing to notice, just to help you to try and remember it, is as you come down the group, they actually become darker in colours. We start with the yellow, the green through to the red brown through to the grey. Okay, so there's some key properties. These, if you remember, group 7 are diatomic. That means if we use fluorine as the example, they always go around in covalent molecules. So covalent means they're sharing a pair of electrons, and as F2, Cl2, Br2, I2. If we're drawing that little review of covalent bonding, that means they are going to share. So if I put my dot electrons here, this could be fluorine. Fluorine's got 7 electrons in the outer energy level, so 1, 2, 3, 4, 5, 6, 7. 7's not stable, so it needs to share one. A second fluorine comes along, it also shares one. And we have got 1, 2, 3, 4, 5, 6, 7. Now it's sharing, it's got 8. They've both got 8. Here we have a molecule of fluorine, diatomic, and these will all work in the same way. It's also worth remembering that, where I've got this on, that the test for chlorine, so if you want to test a gas, see if it's chlorine, what we can do with this one is we can use a piece of damp blue litmus, and if the damp blue litmus comes into contact with the chlorine gas, then the litmus will actually be bleached, it'll turn white, and that allows us to prove the gas is chlorine. I've got a little video that shows that, so we'll put that in somewhere later on, just so you can see it visually as well. We also need to know, with the halogens, some reactions. So the first reactions we need to know are the reactions with metals. Okay, so you need to know how these halogens react with metals. So let's have a quick look. We have got a metal, let's do it in a general equation first, plus the halogen, and it makes a metal halide. So if, for example, the metal is sodium and the halogen is, I was going to do chlorine, but let's do fluorine. We'll use chlorine later on. Fluorine, then we end up with sodium fluoride. Let's put it into symbols. So sodium is Na plus fluorine, remember diatomic, so it's NaF. Sodium fluoride, NaF, and we've got to balance this, so there is 2 F's here, there's only 1 here, so we need a 2 there to make it 2 F's, that gives us 2 Na's, and therefore we need 2 Na's here to make that balance. If you're wondering how we've got this formula, NaF, please just go back and have a look at the valency video, and that shows you how we work out those formulas. Other reactions that we need to know, so let's just swap my sheet. Other reactions we need to know, we need to understand the reactions with hydrogen. So here we have got reactions with hydrogen. Okay, so we're going to react these with hydrogen. Let's do a general equation first. So we have got hydrogen plus the halogen, and it forms a hydrogen halide. So in words, that will still be hydrogen. This time I will use chlorine. So there is my chlorine. So it makes the hydrogen halide, so it's going to be hydrogen chloride. Hopefully you spot hydrogen chloride. We've come across that before. Hydrogen chloride is an acid. Hydrochloric acid, so we've got this. This forms HCl. Remember, these are diatomic, so it's 2 and 2. That means we need to balance it. That means we need 2 of these. And if we take this and dissolve it in water, then it forms a solution which is acidic, okay, indicating the acid properties of the hydrogen halides in this example. And we also need to look at a second type of reaction with these, and we need to look at what are called displacement reactions. I'm just going to swap my sheet again and see if we can get as much of this next one on one page. So if we look at the next little bit, and here we're looking at displacement reactions. Now remember, displacement reaction is when one element pushes out another element from its compound. So displacement reactions is one element pushes out another element from its compound, and that's because the element is more reactive and it's pushing a second element out. So let's have a look at an example. Here we've got chlorine plus potassium bromide. Okay. Now in this example, chlorine is more reactive than the bromide. So what's going to happen here is the chlorine is going to push out the bromide from this. So the potassium is now bonded with the chloride, and the bromine has been pushed out or displaced. In terms of doing this as a symbol equation, chlorine, diatomic Cl2, potassium bromide, potassium's K, bromide Br, KBr, potassium chloride, KCl, and bromine, remember it's diatomic, is this. Now that isn't balanced. We've got 2 chlorines, only got 1, so we needed 2 there. And we've got 1 bromine here, and we've got 2 here, so we needed 2 there to make it balanced. We've got a balanced equation. So just remind ourselves, this is displacement because this is a more reactive element, and it's pushing out the bromide from here to leave the bromine on its own, and then the potassium chloride has formed a new compound. If we were to do it again, let's do another quick example. Let's say we have, just do it in symbols, so we've got the chlorine again, this time with potassium iodide, so Ki. What's going to happen with this is the chlorine is more reactive, so we're going to form that. It's going to be displaced, and that's going to push out the iodine or the iodide ion to form iodine. Again, we've got to balance it, so 2 and 2. Notice that these equations are very similar, they're identical in terms of structure. We've just got to swap the elements to get the right elements in place. If you were to do something like this, so bromine with potassium chloride, so what we're doing here is we're starting with the reverse of this. So here's my bromine, and what this bromine is trying to do is push out the chloride from the potassium from the compound. It's unable to do it. It can't do it. So this is no reaction. So we can use this information to construct a reactivity series in order showing the most reactive down to the least reactive of these. And it would look like this. So we have got, there's my halogens. Let's have my compounds. So we've got KCl, KBr, potassium bromide, and potassium iodide. If we just turn it into a little table, so it will help us to see visually what's going on. So there we are. We always start this table because with crosses in, because we don't need to react these two together, they're the same. reactivity. So we would start it like this with those already in place. And if you remember, if chlorine is added to potassium bromide, we've got that equation here, chlorine with potassium bromide. We know it's going to react. This is more reactive, so we put a tick in that box. This, again, we've got an example on here, is going to react, yes. But the bromine, we've just shown here, does not react. And if we were to do the bromine with potassium iodide, we would see a reaction. But the iodine would not react with either of those two. So what this allows us to do then, is it allows us to say that the chlorine has got 2 ticks, therefore it is the most reactive. Bromine's got 1, therefore it's the next reactive, and iodine hasn't got any, therefore it's the least reactive. So we've put those in order, as we've just said. You notice that is the same order that they are in group 7. And if I go up that group, then what I'm seeing is the reactivity is increasing. So they are becoming more reactive as we go up the group. Reactivity is increasing, which is the opposite to group 1. Group 1, you go down the group, become more reactive. Group 7, the halogens, you go up the group, they become more reactive. If we were to chuck in a stantine at the bottom, let's just have a little think. What would happen here based on this pattern? We can see that a stantine would sit down here, therefore it's going to be the least reactive. So we would expect that to be no reaction, and no reaction. We wouldn't expect to see anything happening with stantine because it's the least reactive in group 7. These reactions that we're looking at, we're going to have a quick look in a bit more detail at them, because these are redox reactions, so it links back in with a little bit of work we did on electrolysis in the previous unit. Let's just swap this over. So if I just write one of these equations out again, let's use this one. So this is chlorine with potassium bromide. Let's balance as I go, making that and producing bromine. So there's my equation. Let's just split this for 1 second. This is KBr, and this side is K plus Cl minus. And you can notice that the K is a potassium ion here, and it's a potassium ion here. So that is not changing during the reaction. So what I can do is remove that. Remember, it's called a spectator ion. I can remove that from the reaction. So my reaction becomes chlorine, because chlorine doesn't exist on this side, so that's changed. So I've got my chlorine. Then I've got my Br minus. I'm going to ignore this. I'm going to need 2 of those to make it balance, forming 2 lots, ignoring that, of Cl minus, and the Br2, that's left in because that doesn't exist on this side of the equation. So they're the chemicals that have changed during that reaction. Let's just think about what this means in terms of oxidation reduction. So if I just put the word here, orig, that should hopefully jog a few memories that oxidation is loss of electrons, reduction is gaining electrons. So if I pick on the chlorine first, so the chlorine does this to become a negative ion. If it's becoming a negative ion, what has it done? We've actually gained electrons. And if we've gained electrons, if we use this, gaining electrons is reduction. So this process here is reduction. Why is it reduction? Because there's been a gain of electrons. If we look at the bromide ion, so here's my bromide and here's my bromine. What's happened here? It's gone across during the reaction into change. This is a negative, and now it's lost its charge. So it's losing a negative charge, so it's losing electrons. Oxidation is lost. So this side is oxidation, and we have a loss of electrons. We're losing electrons during that process. I think you should have a try of one of these, because you need to be confident with these. So here is Br2 plus I minus. Okay, you have a little think. You could pause the video there for a second, have a little try at that, see if you can work out what's going to happen using the format we've got above. I'm going to give you the answer now, but if you pause the video, then you can try it yourself in a second. So what's going to happen here is the bromine, if you remember, is more reactive. So the bromine is going to be able to take the electron from here to form the Br minus. And that's going to release or displace the I2. Got to make it balanced, so you need 2 and 2. And we can see now in this example that if I look at the bromine has formed a bromide ion. How's it done that? It has gained electrons, gaining electrons, therefore that is reduction. And the iodide started off with the electron, it has now lost the electron, so it's no longer negative, it's lost the electron, that is oxidation. So you've got both happening again, reduction, oxidation, so it's a redox reaction. So the displacement reactions are redox reactions. So let's explain these equations, why this happens. As you go up this group, they become more reactive. Let's try and understand why. So here's my nucleus for fluorine, here's my nucleus for chlorine. Fluorine's got 9 electrons, that is 2, 7, and chlorine has got 17 electrons, so it's 2, 8, 7. What do these want to do? Well, neither is stable, so what they want to do is they want to gain 1 electron during the reaction, so I'm trying to gain an electron. And if you think about it, to gain an electron, then the electron is going to be added into the outer energy level, and it's going to be easier for fluorine because that is a distance that is shorter than that distance. So the outer electron is going to be added to the nucleus, or added, sorry, to the energy level that's going to be nearer to the nucleus, so there's greater attraction. Whereas in this example, chlorine, the outer electron is being added to an energy level, but the distance is greater. So there's a greater distance, therefore there's less attraction, therefore it's not as easy to add that electron. So the key things to think about here is these are trying to gain electrons. You need to think about the distance, so that as they become smaller, the distance gets less. If the distance gets less, then it's easier to add that electron, and therefore they become more reactive. So they become more reactive as they go up the group. So just remind ourselves, we've got group 1 and group 7. Group 1, as you go down the group, they become more reactive. And group 7, as you go up the group, they become more reactive. Okay, that's the second video then on halogens. We're going to do a third video on noble gases, put them all together for you, so then you've got all 3 key groups of the periodic table available.